Hello and welcome back to Unit 4. In this portion of Unit 4, we're going to introduce Newton's third law. Now, the first and second laws have to do with how motion happens and when motion happens. Third law is the first time when we're going to be able to look at what happens when objects interact with each other. To begin with, I would love to show you these videos, but I'm worried about issues associated with that encountered last week, shall we say. So instead, I will put these links on Brightspace for you to view. Both of them show similar activities where you have two trains that crash into each other, and it's really dramatic. And the point I like to make with this is that when the two trains crash, both trains get damaged. They both experience a force. Not a huge surprise. But that is true whenever two things interact. They both experience a force. This is because of Newton's third law. Newton's third law states that whenever one object exerts a force on a second object, the second object exerts a force equal in magnitude but opposite in direction to the first force. There are many shorter ways of saying this that occur in everyday language, if you will. One of the most common is the equal and opposite reaction version of Newton's third law. For every action, there's an equal and opposite reaction. I do not like that statement because when you think about everyday language, you have something happen and then the other thing happens as a reaction. You know, somebody calls you a name and your reaction is to maybe get mad or blow it off or whatever, right? Something happens and then something happens. That's not what happens with Newton's third law. These two forces happen simultaneously. And they happen for the exact same amount of time. Okay? I can't have one force happening for longer than the second. The interaction between them has stopped, or it starts as soon as the one thing's you get, I hope, what I'm trying to say. I don't really know how to say it. The interaction times are the same. Exactly identical. They start and stop exactly identical times. So now we have all three of Newton's laws. Really quick, just as a reminder which each of them are. First law has to deal with what happens when there is no net external force, and that's the object will have a constant velocity. Second law tells you that if there is a net force, the velocity changes, and that force will equal the mass multiplied by the acceleration. And third law again has to do with the interaction of the two objects, and one force will be equal and opposite to the other force. And as you can see from third law, we have two forces. They come in pairs. So how do you identify a third law force pair? Okay, well, it must be equal in magnitude. It says it right there in the statement of Newton's third law. They are equal in magnitude but opposite in direction. This, however, while must be true, isn't usually very useful in identifying a third law force pair. Usually you identify the pair and then say, because they're a third law force pair, they must be equal. Okay, so how do you identify the pair? Okay, well, look at the direction. They must point in opposite directions. Have to. They must result from the interaction of two objects, which means they must be on two free body diagrams. If you have two forces that are equal and opposite, but only on one free body diagram, those are not a third law force pair. Things that I like to look for. Remember I said I love my subscripts. Okay. Flipped subscripts. Okay. Why? Because you have the force from object A acting on object B, and you have the force from object B acting on object A. Two objects, the same interaction between those two objects. Not only that, but it must be the same type of force. So if it's a normal force, it has to be a normal force. If it's a gravitational force or weight, it has to be a gravitational force. You can't have a third law force pair to a normal force that is a tension force. It doesn't work that way. It's not the same interaction if one's a normal and the other one's a tension. Okay. So let's look at examples. Let's go back to our two stacked blocks. Before we had people pushing and pulling on this. Make it simple. And let's look at the bottom block again. I'm going to label my free body diagram because I'm going to draw both. You might recall that we had three forces on the bottom block. We had the gravitational force downward, the normal force from the top block on the bottom block downward, and we have a normal force from the ground on the bottom block pushing upward. Okay. If we now draw the free body diagram for the top force, there are two forces there. We have the weight of the top block, and we have the bottom block supporting it, pushing upward on it. Now I have two forces, and if I look at them, I have this one and I have that one. They are the same type of force. They're both a normal force. One points up, the other points down. One is from the top block on the bottom, the other one's from the bottom block on the top. So they meet all of my criteria that they're the same type of force. They're on two free body diagrams. They're the same two objects interacting as indicated by the subscripts. Okay. These are a third law force pair because they are on, or because of this, those two forces must be equal in magnitude. Must be, no choice. Okay. All the other three that we have listed here have third law force pairs, but I would have to draw additional free body diagrams to find them. So for example, this one and this one are both caused by the Earth. Therefore, I would have to go look at the Earth's free body diagram in order to find the third law force pair from this one. This one is on from the ground. Well, depending what we mean by ground. Okay. Is ground actually ground? Is it part of a house, maybe a floor in a house? Is it a shelf? We need to go look at whatever that second object's free body diagram is. There's a possibility that by ground, what we really meant was earth again, but it's earth used in a different manner. Okay. If I wanted to identify the third law force pair to say the weight of the earth on the top block, then its third law force pair would be a gravitational force, a weight from the top block acting on the earth. Flip the subscripts, and I have my third law force pair. Okay. Okay. So why don't they have the same effect? Okay. I was once driving down the interstate, and this rather large green bug somehow managed to come in through my driver's side window and smash on the inside of the back glass of my car. My car window is fine, still is. That bug did not survive this. So if the forces are equal, why don't they have the same effect? And to illustrate that, rather than using a bug, I'm going to use this little guy who I call Sir Speedy and a semi-truck. Now, Sir Speedy, while very cute, doesn't always make the best decisions, and he's decided to play chicken with our semi-truck. For those of you who might not know, when you play chicken, it's when you line up facing each other on the road and drive at each other, and the first person to flinch and veer out of the way is the chicken. As I said, Sir Speedy is not the brightest little guy. Okay. Well, the Mack truck, the big truck here, the Mack truck, does not care. He's big. He's made of steel. You know, Sir Speedy may not be the brightest person, but he's got lots of courage, and so he doesn't flinch either. So these two do collide. During the collision, let's look at the forces on the truck. So we have a normal from the road on the truck. We have the truck's weight, and we have a normal force from Sir Speedy on the truck. Now you may be thinking there are other forces here. Well, wouldn't there be friction or something like that? Yes, but friction is caused by motion, and the amount that the truck is going to move during the actual collision with Sir Speedy is very, very small, and therefore friction for that very short time during that interaction can essentially be ignored. Okay. If we look at Sir Speedy, we have a very similar free body diagram. We have a normal from the road, we have Sir Speedy's weight, and then we have the normal from the truck on Sir Speedy. And if we look, there hides our third law force pair. And because we are ignoring friction and anything else that might be happening horizontally, those are the only forces acting on these two vehicles horizontally. Therefore, those two forces must cause the net force on these two objects. So if we look at the truck, F net equals the mass of the truck times the acceleration of the truck. So we're left with this. If we look at Sir Speedy, F net is the mass of Sir Speedy times his acceleration. Okay. Now, by third law, this and this have to be equal, which means mass of truck times acceleration of truck has to equal mass of Sir Speedy times the acceleration of Sir Speedy. But look at them. This guy is little. He's probably in a fiberglass or aluminum-bodied, lightweight little car, whereas this truck is going to be made of nice, strong steel. Okay, so there's a couple things that come from that. One is the mass of the truck is going to be much greater than the mass of Sir Speedy. And because the mass of the truck is going to be much greater than the mass of the Sir Speedy, the acceleration of the truck will be much less than the acceleration of Sir Speedy. Okay, which is bad for Sir Speedy. Right? The other thing that happens, which is kind of going back to the bug hitting my window. How much force can a particular item withstand? Okay, which has nothing to do with third law. Nothing at all to do with third law, but everything to do with what the effect of that force is on the object. Okay, well, which is going to crumple first, fiberglass or an aluminum versus steel? So the same force can do much more damage on the smaller object than it does on the larger object. Okay. So a couple of things that come out of here. One, you have to think about what effect does the mass have? A larger mass will have a smaller acceleration for the same net force. Okay. Which plays a role in third law. The other thing you have to think about is what would the effect of any force be on that object? Some materials can withstand a bigger force than others. Okay. Moving onward. Here we have a cup sitting on a table. If I think about the forces on the cup, I have a normal from the table on the cup, and I have the cup's weight. Now, assuming this is a normal table sitting on the ground, then the acceleration is 0. So if I look at the forces here, I'm going to have normal from the table on the cup in one direction. The weight is in the other direction, so I'm going to subtract that off and let that equal mass times acceleration, except there is no acceleration in this case. It's just sitting there. In which case, the normal force will equal the weight force. Okay, so we have two forces. They are equal. They are opposite. Are they a third law force pair? And you might think so, but they are not. Okay, why are they not? Remember the criteria. Okay, two free body diagrams. We only have one. These forces are acting on the same object. Okay. Flipped subscripts. Okay, which is indicative that it is the same two objects interacting. Here we have three objects. And I wrote a T for table when I should have been writing a C for cup. I am sorry. Let me fix all my subscripts. Okay. Flipped subscripts. We have the table, we have the cup, we have the earth. These are not flipped subscripts. They must be from the same interaction. Good way to check if it's the same interaction. One, check the subscripts, but check and see if it's the same type of force. Is it the same type of force? No, you have a normal force and your weight force. Okay? These do not meet the criteria to be a third law force pair, even though they are indeed equal and opposite. To help illustrate that, consider a really odd table that happens to be sitting in an elevator. I know, it's a little bit of a stretch, but consider a table sitting in an elevator. If we now consider the cup sitting on the table in the elevator, we now get that the normal force is bigger or potentially smaller than the gravitational force, depending on what that acceleration is doing. Okay, the acceleration could be up or could be down, so it could be bigger or smaller. Only when the acceleration was 0 did our forces equal each other. Okay, our two forces are equal, yes, but they're not equal because they're a third law force pair. They're equal because of second law and the fact that the acceleration is 0. Okay. We've been working with external forces, forces that come from outside an object. What's the opposite of that? What is an internal force? So let's look at this situation. We have two blocks, again, red and kind of yellowish. And let's consider the free body diagrams of these two blocks separately. We have a normal from the surface on the red block. We have the red block's weight. We have a normal from that hand pushing on the red block. And we have a normal from the yellow or greenish block pushing on the red block. And there might be friction and things like that, which I'm going to ignore because they're not necessary for the point I'm trying to make. Okay. If we look at the yellow block, we have a normal from the surface on the yellow. we have the yellow block's weight. We have a normal from the red block on the yellow, and that is it. The hand is not touching the yellow block, so that doesn't occur there. Again, we're ignoring anything like friction and things like that. They're not necessary for the problem. And we can see our third law force pair hiding right there. Now, pretend you thought these were two separate blocks, but unbeknownst to you, they've been glued together. So instead of being two, it's actually one. Well, if we think about this as one object, what do we have? We have a normal from the surface on the combined object. We have the combined object's weight. If we come over here, this would be the mass of the red one times G. This would be the mass of the yellow one times G. This would be the combined mass times the acceleration due to gravity. And where we have the hand pushing on the combined blocks. Okay. Where did our third law force pair go? Well, when we considered each block individually, they were external to each block. When we combined them and considered them as one unit, they're now internal to that unit and canceling each other out and not needed for any analysis. As you will see as we work problems involving third law, how you view your system, the group of objects that you're looking at, will determine what forces you can find. If in this example, I was only considering what was the acceleration of the combined system, then I'd look at it as one combined system. If, however, I wanted to know how big was the force between the two blocks, then I would be looking for this third law force pair, and I'd have to come over and look at the two blocks individually. Okay. To finish up this part of Unit 4, I want to take a minute and think about how Newton's three laws play into this scenario. You're in a plane, and as it accelerates down the runway during takeoff, you feel like you're being pushed backward into your seat. Okay. How can we use three laws to explain that? Okay, so let's start with third law. Okay. The normal from you on your seat is equal and opposite to the normal from the seat on you. Okay. First law. First law says that you're going to have a constant velocity unless your net force doesn't equal 0. Okay, well, you're sitting on this seat and you're trying really, really, really hard to maintain a constant velocity. Okay. Well, if you think about at first, your velocity is 0 and you're trying to maintain that constant 0 velocity. But you also have this piece. This piece says that the net force on you has to equal the mass times the acceleration on you. And that acceleration is going to be caused by the fact that the seat is pushing on you. So you're feeling like you're being pushed back into your seat. That's not really what is happening. What's happening is you're trying to maintain your velocity and the seat is moving forward into you, causing you to accelerate with the plane. This concludes this part of Unit 4.